Good morning, everyone.
Good morning, sir.
Good morning.
Good morning, sir.
So I have a little bad throat today, so I will try. We may, end today's session little early. I hope it is fine with you guys. Okay, so two more kinds of convex function, uh, which are any of the properties of convex also works on them. So by definition, these are pseudo-convex called pseudo-convex function. In fact, they are together only. So definition is let so read the definition and then we will discuss a little bit. So I have Is the definition clear? So actually it looks something like this. So pseudo-convex function. I mean, in case of we know that if it is completely convex, its structures look something like this. Is it visible? What I have now? So pseudo-convex, I mean, they look very close to convex. That's why they actually, you can say that they close to convex. So we assume that they almost follow most of the properties of convexity as is concerned. Suppose I take 2 points. This is my x1, this is my x2, and another one here. This is my x1, this is my x2. If I draw del f function here, gradient function, it would look something like this, and x2 minus x1 is in this direction. If I take, suppose इसको दूर करते हैं, so it looks nice, something like this. My del f is in this direction, and the vector in this direction. So you can look at the angle and see how whether it is greater than 0 or positive or negative, these two statements becomes true. Can you visualize it? So this one is case 2, otherwise this one is case 1, because fx2 is greater than fx1. So first statement is true. Here fx2 is less than fx1. So second statement. Just it makes sense. Is this fine, guys? If it is fine, we can move to the next definition. It's called quasi-convex function. So for pseudo-convex, differentiability is important. Okay. Then only we can show a person that is pseudo-convex or not. As far as quasi-convex is concerned, Read the definition again. So see here we are not assuming anything about differentiability or open convex set. Graph for this one looks like so you can see there are discontinuity, non-differentiability, all kind of situation can arise. Still, the structure is somewhat close to convex. So if you take any 2 points, suppose I take point on this side and this side, if I connect it, so this is my x1, this is my x2. So suppose some x which is lambda x1 plus 1 minus lambda x2. So if I take this point, in this case, actually both of them are greater, but anyway, fx2 and fx1, I will take maximum of these two. So I can say another point we can consider is, let's say, here and here, and connect it. So any one of them between fx1 and fx2, the convex combination of functional value will always be less than equal to maximum of functional value at each of the points. Then we can say it is a quasi-convex function. Is it clear, guys? Any questions? So study of convex sets and convex function, I stop here. For more detail, as I have said in the book, there are a lot more information, but we cannot really diverge into everything there. So now I will move to unconstrained optimization.
This is known as quasi-convex function.
Yes.
Actually, you have written quasi-concave in the just above the figure that you will.
Read it properly. Minus f is quasi-concave.
Okay, sir. Okay, sir.
So this will be uploaded. Let me start now unconstrained optimization. Just give me a second. Let me do those initials.
So is there any relationship between convex function and with these functions? Means are these a special case of convex functions?
Yes, they are actually. So in the book, if you look at it, they have shown a very beautiful, diagram. If you want, I can upload it also. So these are special cases of convex function only. Many a times, see, real world problems cannot be always convex, right? So these are very close to convex.
Yes, sir.
That's why we meet most of like when it comes to global optimality and all, we can assume that whatever is applicable to convex works here as well.
Okay.
So good morning, sir. Can you hear me, sir?
Yes.
Sir, in this quasi function, you have it is mentioned that maximum of fx1 or fx2 will be it will be compared with the f of lambda x1 plus 1 minus lambda x2. But will there be a situation in which any of the fx1 and x2 can be less than that value? We
If
have
there's
to
a
compare.
situation like that, then it is not a quasi-convex function.
Sir, we have to compare the max of both of them, na? Max of f of x1 and f of x2. If any one is more than f of lambda x1 and 1 minus lambda x2, and suppose x2 will be less than, then
Just let me write it again here. So what we are discussing is f of lambda x1 minus lambda x2 should be less than equal to max of fx1 comma fx2. So what is your question?
my question is among fx1 and fx2, we are choosing the maximum one. But will there be a situation when the maximum will be definitely greater than this f of lambda x1? Suppose fx1 is greater than fx2, but fx2 might be less than f of lambda x1 and 1 minus lambda x2. Is it possible?
Then it is not a quasi-convex function.
So here we are comparing only f of x1 and x2 with this value, na?
See, suppose, let me show you a curve. Okay, something like this. So, something like, okay, I take a 2 points, x1 and let's say x2 here. And to ignore, we take x1 here and x2 here. Their combination, convex combination lies here. Let's call it x. Is that fine?
Yes, sir. Yes, sir.
Now this f of x is greater than both the maximums. I mean maximum of fx1 and fx2. Then it is not a quasi-convex function. For it to be a quasi-convex function, this inequality should hold. That's the definition, right? So I'm
Sir,
not
I
getting
understood it should be either greater than f of x1 or greater than f of x2. It should be greater than both. It should be less than both.
Just a second, Moingini. There are two numbers, fx1 and fx2. Suppose this is 3 and this is 5. What is maximum of fx1 and fx2?
5, sir.
5. So there will be one value only, na?
But if f of x is 4, sir, what will happen?
If f of x is
4.
So this is less than 5, it is a quasi-convex function.
But it is greater than 3, na, sir? So will it be okay? That is what I'm asking.
What does max operator does?
Max operator gives us the maximum value, na? But
maximum of any one of them.
Any one
so
of
it
them.
can, even in this case, when I was trying to show you, suppose this type of case here. This is x1 and this is x2. Between x1 and x2, max of x2 lies here, right?
Yes,
x1.
So
this suppose
is
this is 3, 4, 5. So that, yeah, so max is just max of fx1 and fx2 is either fx2 or fx1. It should be greater than. The idea is the you know, when you look at all the points, convex combination of all the points between these two x1 and x2, it will always be less than the one of the maximums. So it is giving you a non-decreasing, monotonically increasing kind of trend. Does that make sense?
Yes, sir. But in this portion between x1 and x2, it looks more like concave, na, sir, not convex. The function. It has a maximum within x1 and x2.
Which one?
The green one that you stated just now.
Maybe I'm not able to draw it properly, but idea is this small nicks and hills, small, you know, between when you're trying to go up. It is a representative image, right?
Okay, sir.
If it becomes concave, if a function looks like this, it is not a quasi-convex function, right?
Okay, sir.
But if I define my set between these 2 points and removing this part, yes, it is a quasi-convex function. Make sense?
Yes, sir. Thank you, sir.
Okay, you do a little bit of homework, study it more properly, and then we can discuss if you have any questions.
Sir, I have one question. Sir, in case I have an inflection point or a saddle point, so can I say that I need to only check for the saddle point for x1 and x2?
Hello, seems I was dropped. Someone was saying something?
Yes, sir. Sir,
Yes.
actually, I was asking whether if in case the function has an inflection point or a saddle point.
Let me tell you one thing. First, you do your homework on this part. I have explained you the function.
Yes, sir.
You think about it, study it. If you're still not clear, then we can discuss. Okay?
Yes, sir.
Thank you. So going forward with unconstrained optimization. So the moment we say unconstrained, we are looking at minimizing some function fx. And I'm not putting any constraint like that it is a convex or anything. I'm minimizing a function fx such that x belongs to some set. Okay. This is what we generally look at a optimization function. But when I'm talking about unconstrained one, optimization, we are looking to minimize f of x without any constraints. Does that mean that I should get rid of this? No. That is the set on which sometimes it will be just given you minimize fx equals to x square. That also falls under your unconstrained optimization. It could be minimize fx equals to x minus 2 square, x is between 0 and 2. Okay, so sometimes x vector is given on that also. We still consider this as a unconstrained optimization, but by definition, this is more appropriate, representation of unconstrained optimization. So what we want to see is, first we want to understand unconstrained optimization, how it works, and its logical extension is constrained problems or constrained optimization when we have minimize fx. A more generic representation of constraint problem is such that g of x is less than equal to 0, h of x equals to 0, and some x belongs to s. So we have inequality constraint, we have equality constraint. So this is a more general representation of your constraint problem. Okay, so interesting thing is, this constraint problem is, if you look at it, we will also look very soon, is a logical extension of these problems, where we will see that even when we are solving using first order condition or numerical methods, we end up solving one of the unconstrained problem. So to continue with unconstrained problem, there are two things which we need to understand. First is necessary optimality condition. Second is sufficient optimality condition. As far as definition of unconstrained problem optimization is concerned, we say, we write in definition here so it is clear. Consider the problem of minimizing f of x over Rn, and let some x bar belonging to Rn if same thing which we have studied general case of when we started the minimizing of convex function. If fx bar is less than equal to fx for all x less than equal in the set Rn, then x bar is called global optimal solution or global minimum, assuming that we are going with minimize fx. If there exists epsilon neighborhood and x bar around x bar such that f of x bar is less than equal to fx for each x belonging to neighborhood of x bar, then x bar is called local minimum, as we have already seen. And third one definition is while f of x bar is less than fx for all x in the neighborhood of x bar and excluding x bar itself for some epsilon 0 greater than 0, then we have see what is this one is called based on what we have discussed last class.
Strictly local.
Strict local minimum. So a global minimum is also a local minimum or not?
Yes.
Yes, sir.
Yes. So in its neighborhood, it is a local minimum, and amongst all the local minimum, the one which gives you the most desirable value or the minimum value of your function, we call it global minimum. So study of optimization actually is more about, finding those local minimum. Once we know all the local minimum, it is not that difficult to find the global minimum. Does that make sense?
Yes, sir.
So we'll start with necessary. Necessary. Is this correct spelling of necessary? Necessary, huh? Optimality condition. So whenever we talk about optimization, we talk about two things: necessary condition and sufficient condition. What is your understanding of necessary and sufficient? Just in literal English meaning. So to study at IIT Kharagpur, undergraduate in IIT Kharagpur, what is the necessary condition?
JEE qualified.
Can you be a little louder, please?
The JEE entrance exam qualified.
Okay. So can we say if someone has clarified JEE mains is the necessary condition and sufficient condition as someone has qualified JEE advance? Do you see the difference?
It is necessary, but it is not sufficient.
It is not sufficient. So JEE means actually is a necessary for you to study at IIT JEE, IIT Kharagpur, any of the IITs, but it is not sufficient. For sufficient, you also need to clear JEE Advanced. So in the same spirit, I will try to explain you necessary, optimality, and necessary and sufficient optimality conditions. So necessary condition, many of us already know. We have been studying it since class 12th. It is also known as FONC. I don't know. Have you heard this term? It is called first order necessary condition. What was first order necessary condition? From going back to differential calculus 101 class 11th. अगर किसी फंक्शन का मिनिमम निकालना है तो पहला चीज हम लोग क्या करते हैं?
Differentiate it.
Just differentiate it, right? And equate it to 0. At that time, we do not even care whether the function is convex, concave, or what, right? First thing that comes in mind whenever we see a function, what is that? Differentiate kar do. Equate it to 0. All of you agree? You agree? That's how, I mean, if you remember simple mathematics, you've been asked to minimize x minus 2 whole square. You just 2x minus 2 equals to 0, x equals to 2, right? This is the first order necessary condition for local minimum to exist. Now, second order necessary condition is, now you got this number x equals to 2. Okay. Now, how do we know whether it is a minimum point or maximum point?
By finding the second derivative, we will check whether it is greater than 0 or less than 0 by substituting this point at the f double W.
So this x equals to 2 does not tell us about the curvature of the function. Whether, I mean, we know it is like this or it is like this. So that is why second order necessary condition is required. So suppose that f is r into r is twice differentiable. For this to exist, I need twice differentiability at x bar. If x bar is local minimum, then del f x bar should be equals to 0 and Hessian at x bar should be positive semi-definite. So what we are checking, first we are equating it to 0, then we are taking we are finding our x bars. In this case it was easy. In some cases you can get 2 or 3 values, x bar equals to 2, x bar equals to 3. Generally you put a star here, or x bar equals to -1, something like this if you got. Okay, so second thing, you need to find Hessian at each one of these points. If you know the Hessian at each one of these points, and if it is positive semi-definite, I can tell that which one is the local minimum. Is this clear so far?
Yes, sir.
Now coming to sufficient optimality condition. Before I tell you sufficient optimality condition, let me go back to necessary condition again and tell you necessary condition must be true for every local optimal solution. You agree?
Yes, sir.
Yes, sir.
But it could be possible that the first order the necessary condition which you have found is not a local minimum. When is that case possible? It could
Sir,
be just an inflection point. Yeah. Nicholas, right?
yes. If it is other than positive semi-definite.
It could be that it is just an inflection point. Even at the inflection point, it will give you del fx equals to 0.
Yes, sir.
So necessary condition must be true for every local optimal solution. A point satisfying this condition need not be a local minimum. Although it satisfies that del fx equals to 0, but there are places like inflection point and all, it will satisfy, but it is not a local minimum. So sufficient condition state, suppose that f r into r is twice differentiable at x bar if LF of x bar equals to 0 and hx bar is positive definite, then x bar is strict local minimum. Read the statement carefully. We'll be back in 1 second, guys. So just read both the statements carefully. Can you see the difference? Because both of them ends up saying the same thing. Read both of them carefully and then we'll try to discuss it. So what is the difference you are finding between necessary and sufficient condition, language wise?
Sir, in necessary it is positive semi-definite. Hertzian. In sufficient it is positive.
I mean, apart from that, because I am talking about strict one. So see, if you read the necessary condition, if x bar is a local minimum, then del fx bar will be equals to 0. Read now sufficient optimality condition. If del fx bar and hx bar is positive defining, then x bar is a strict local minimum. Do you see the difference? So necessary optimality condition, we are trying to find those points which are can satisfy the local minimum condition. But in sufficient condition, we are trying to say that if this is true, then x bar is strict local minimum. Now read again both the statements FOMC and the sufficient condition. Do you see the difference now? If x bar is local minimum, then these two will be true. That's what I'm saying in necessary optimality condition. Here I'm saying conversely, if these two things are true, then x bar is a strict local minimum. Do you see the difference?
Yes, sir.
Yes, sir.
There is one small extension because many a times even with twice differentiability, we cannot say anything about the function's optimality. So there is one theorem, at least it holds true for univariate function, that I will give you. If f r1 to r or r to r, let me write r to r be infinitely differentiable, then any x belonging to S is a local minimum if and only if either Fj x bar Fj x bar equals to 0 for all j 1 to 1 comma 2 comma as much infinitely differentiabilities, or else there exists an even n greater than equal to 2 such that fn x bar is greater than 0 while fj x bar equals to 0 for all j between 1 and this number, even number n. Fj is jth derivative, jth order derivative. Read this theorem. We'll just see one very nice example on this one, how it is important. Other than here. Let's try to understand this theorem using this example. So I want to minimize f of x square minus 1 whole cube. Is it okay, guys? Go ahead, try whatever you have learned so far and see what is happening. So find del f, hx and see which points are local minimum, which are not, and give me 5 minutes break also, and to soothe my throat a little bit. So you go ahead and do del f, or if you want, you can also take a break. We'll meet again at 11 and then we will do it. Thank you, guys. I hope you guys are back. So let's check the necessary condition first. So what is del fx here? Equals to? Is this correct, guys?
Yes, sir.
What is hx? In this case, it is just univariate function. Del dash x is how much? So first we will differentiate this, guys, keeping this one constant. So 6x into 2x.
Sir, another 2 will be there, sir, in first term.
Yeah, right. 2 from there and there. So 24x square into x square minus 1 plus 6x square minus 1 whole square. Now, if we equate del fx equals to 0, what are the points we will get?
So 0, 1, minus 1.
0, 1, minus 1. Now see which one of these is satisfying the first order necessary condition. Sorry, second order necessary condition. Which one of these are satisfying? So I need everything greater than equal to 0.
1 minus 1.
All of them are satisfied.
Yes, sir.
So this is my, from FOMC, I have got my points for second order condition, necessary condition. I have got candidate point as 1, minus 1 and 0. Now let's look at the sufficient condition. Is H1 satisfying sufficient condition? What is H1? Let me put F double dash 1. What is F double dash 1 equals to?
0.
What is F double dash minus 1 equals to? Again 0. F double dash 0 equals to 6. Is this correct?
6. Yes, sir.
Definitely it is satisfying my sufficient condition. Positive definite. So sufficient condition being satisfied. So definitely it is a strict local minimum. You agree?
Yes, sir.
But I cannot say anything about these two guys, right? So first of all, I want to highlight the difference between the necessary and sufficient condition. Necessary condition is only giving me candidates for local minimum. Do you understand? Where sufficient condition is giving me the local minimum. Do you see the difference?
Yes, sir.
Now, since I can differentiate it further, what I will do, I will go for f triple dash x based on this one, this theorem. So f triple dash x would be 24 into 2, 48 x square minus 1. So 48x into x square minus 1 plus 48x cube plus 24x into x square minus 1. Just check if it is correct.
Yes.
Now let's check f triple dash 1 and f triple dash minus 1. What are the values we will get?
48.
48 and minus 48. Now look at this theorem. Can we say anything about these 2 points? So right now my j is 3. We have taken third derivative. So you see this theorem will not hold, because if you take f(4)(1) and f(4) minus 1, it will be 0 and 0. However, I have found a n, but it is, first of all, it is not greater than 0, and secondly, all other derivatives less than n is also not equals to 0. So we can conclude they are not neither local min at these points, they are simply some inflection points, merely inflection point. So what I wanted to highlight with this example to you to understand the first order, second order necessary condition and sufficient condition. Does this make sense now?
Yes, sir.
Because language wise I understand, even when I have studied first time it was really confusing. So necessary condition only gives me the candidate point, whereas sufficient condition gives me the strict local meaning. Is this clear, all of you?
Yes, sir.
Now, if I had a convex function, what we could have concluded?
This will be the global min.
It will be the global optimal solution. That is the benefit of showing, because any study which we do about any normal differentiable function, we cannot say it is a global optimal or not. Maximum what we could have done, that we have got 3 values here, and suppose all of them are local minimums. So we'll just compare amongst these 3 values, and whichever will give me the best value, I will call it a global minimum. Is it clear, guys? But if it is a convex, I will get your global minimum directly when I'm able to show that the Hessian is positive semi-definite. Is it clear? Any questions? If there are no questions, let's look at some unconstrained modeling and solving it. So there are 2 ice cream sellers. Let's say the nearest is Digha Beach. There are 2 ice cream sellers at a Digha Beach. Tourists are evenly spread. That means uniformly distributed over a 200-meter beach. Choose 200-meter as a unit length. Okay. Suppose, okay, before I get into it, suppose if you are just more from a human psychology point of view, if you need to set up your ice cream parlor, and suppose there is a competition also, there is another ice cream parlor. Where would you guys will end up putting these ice cream parlors on the beach? At what place?
Sir, at the middle.
At the middle. Why?
Sir, I will have both exposure of the ice cream parlor will be most at the middle, and also in case of travel time, that position will give the minimum travel time for the buyer.
So suppose this is the beach. I'm taking unit length, that is equivalent to 200 meters, let's say, and there are two ice cream parlors that needs to be placed. What we generally see, where is the ice cream parlor generally? So people are uniformly distributed here. So Chandni, you are saying that the two guys will end up putting their ice cream parlor at the middle. Is this correct?
Yes, sir.
So get 1/3 and 2/3.
Okay. 1/3 and 2/3. Any other thoughts?
Since it is a uniform distribution, we can put anywhere within this.
Anywhere in this. Okay, now from human psychology, being an ice cream parlor guy, let's say, whether you will put, you do not care about any restriction imposed on you. You only care that I want to maximize my revenue, right? Where you would put. Generally, have you seen many a times if you go to a bazaar, these pawn shops or grocery shops, are they really evenly distributed, or are they, clustered around same area?
So clustered at the entrance or at the
Clustered
exit?
area.
Clustered around the same area. What is the logic? At least what I understand, I will tell you. I want to hear your understanding too. So idea is, if I go to this ice cream parlor and ask for, let's say, strawberry, and if he does not have, I will go to the next one, right? So
Yes.
ideally, when these shops, when they put up in the market, they think that they have 50% share, and whatever will slip from this side will come to me. That is the idea. Whatever, if something is not at this shop, I will fulfill that demand. So I will have more chances of more generating more revenue. Do you agree? Seems you guys do not agree.
Correct.
So that is when as a shopkeeper you will think along this line. But suppose municipality has asked you or the ice cream parlor boys to place your parlors such that the average walking distance for customer is minimum. Now find the position of ice cream parlors. So earlier, when you are placing it here, it was more of a, what do you call, your profit was your objective. Here you have been asked, you need to formulate the problem such that average walking distance for a customer is minimum. So you need to first formulate this problem and then find the optimal solution. Go ahead, try it. Keep in mind that the tourists are uniformly distributed across the beach. no need to take 200 meters. Think of it as a 1 meter length beach, and then we'll multiply with 200.
So then I should put it at 1/4 and 3/4. Can I see that half of the beach will be going to one shop only, and then I can only formulate the problem for one half of the beach?
Sir, in that case, it has to be in the middle only, because if a particular ice cream is not there in one shop, if I keep both the shops in the middle, then it's easier for the customer to go to the next shop because it's just next. Otherwise, if I put it in a different place, let's say 1/4 and 3/4, a customer walks to the 1/4 shop and he doesn't find, he has to cover another 1/2 to go to the 3/4, which will be higher in terms of distance covered. So ideal would be to keep it in midpoint.
I agree, but thing is that you know that is really right from a real life perspective. But what we really want to understand that the average distance covered by the customer is minimum, and assume that both ice cream sellers are selling same ice creams.
Okay.
Okay. So ideally we need to formulate it, right? Logically speaking, what you're saying is right. But if both the ice cream parlors are identical in nature, and more importantly, try to understand the tourists are uniformly spread throughout the beach. So if we want to model, the idea is to learn how to, how to formulate such problems. So let's say I have a beach of length 1 meter. I have to find the places for my ice cream parlor. So what we end up doing here is converting the words into equations. So let's say I'm putting first ice cream parlor X distance from the, let's say this is the point of reference datum, and the next one Y meters from X. This one is 1 minus X minus Y. Is this okay so far?
Yes, sir.
So I want to write an expression for total average distance covered by customers. So if I want to write a function of x comma y as total average distance, how do we write that? So what is the average distance? So just let me define. So all the people on the left of the, let me call it first and this one is second. All the people on the left of first ice cream parlor will go to parlor number 1. You agree?
Yes, sir.
Now, between first and second ice cream parlor, half will go to the first ice cream parlor, half will go to the second ice cream parlor, right?
Correct.
And remaining, these many guys, they have only the option for second ice cream parlor. Agree?
Correct.
Now, I need to find average distance traveled by the people on this side of the beach. How do we find that?
Sir, it should be x by 2.
It should be x by 2. Is this correct, guys? Why it is x by 2?
Sir, sir, I'm not able to explain, but it should be x because maximum is x, and minimum is 0. So average for all the points will come at x by 2 only.
So x by 2 is the minimum distance one person is walking, right? How many people are there? Does this make sense?
Correct.
See, each person is walking the way you have got the average distance each person to walk is right, x by 2. Okay, but each person is walking x by 2. Since they are uniformly distributed, that means there are x persons. So x person will walk x into x by 2. Is it clear to all of you? Whoever is not, it is not clear, please feel free to discuss with me.
Okay.
Hello?
Agree, sir.
Sir,
Yeah.
sir, number of person, how could we take it x? It should be some another variable, no? They are uniformly
But
distributed, but
here, the assumption is the people are uniformly distributed. So x plus y plus 1 minus x minus y will be always equal to 1. So you take as a proportion. That's all we're doing.
right.
Did you understand, Kisan?
Yes, sir. Yes, sir.
See, I'm saying I have taken one unit now. And if the length of this unit is x and they are uniformly distributed, that means there are x people on this side of the beach.
Yes, sir.
Is it clear to all of you? Any questions? Similarly, for this side of people will walk this much and half of this side will walk on this direction. The same logic you can write y by 2 into y by 4. For this one again, plus y by 2 into y by 4. And for this guys, 1 minus x minus y into 1 minus x minus y by 2. Please look at the expression. So if you rearrange these terms, I will have x square by 2 plus y square by 4 plus 1 minus x minus y whole square by 2. Let me know if it is still not clear. Okay, how many of you it is clear that the average distance walked by each person is x by 2?
Yes, sir, clear.
All of you? Okay, I assume that it is clear. Now, how do you find the value of x and y, optimal x and y? Del f by del x equals to 0 and del f by del y equals to 0. How much do you get? Tell me. Just solve it and tell me what are the numbers you have got. So del f by del x will give you 2x by 2 in this side and 2 into 1 minus x minus y by 2 minus, and the second equation will be 2y by 4 and 2 into 1 minus x minus y by 2, and again negative sign. You solve this simultaneously, you should get x bar equals to 1 by 4, y bar equals to 1 by 2, and your f equals to 1 by 4 comma 1 by 2 equals to 1 by 8. When you convert into 200 meters, this will be at 25, this will be at 25 plus 50, so 25, 50, 25, so at 1/4 and from one end and 3/4 from another end. This is where you will place, and the average distance walked by the customer is 1 by 8 into 225 meters. Is this clear, guys? Any questions? If there are no questions, let's look at the another example, very known example, which we do, but many of us do not know that how optimization play a major role in this. Let a sample of data if label is in terms of xi and yi, xi and yi are 1, 2, 2, 5, 4, 7, 6, 10, 8, 40. Okay. Let me change this problem. Let me plot this data in x and y as 1, 2, 1, 2, 4, 6, 8. This is my 2, 5, 7, 10, and 14. So 1 at 2, 2 at 5, 4 at 7, and 6 at 10, 8 at 14. Good so far, guys? Now, I want to find a line which minimizes the sum of squared errors. I want to find a line that minimizes sum of squared errors. That means if I define this line equation to be Suppose this line is y equals to beta, ax plus b. Then f of a comma b is summation I equals to 1 to 5 yi minus axi minus b. So I want to minimize this f of ab. So what kind of problem are we talking about here? All the data science experts?
The regression analysis.
Linear
Sir,
equation? Yeah.
yi minus axi minus bi square.
Oh yes, sorry. We are looking at total sum of squared errors, right? So we want to minimize sum of squared errors. So we are looking at linear regression. How do we generally, if I write y equals to beta naught plus beta 1 x, where x is your independent variable and y is dependent variable, how do we find the value of beta naught and beta 1?
And sir, it will not be bi, it will be just b.
Actually, right, minus b. Yeah, so beta naught and beta 1, how do we find this value?
Slope and intercept.
What is that?
Estimation.
So we use, which is famously known as OLS, ordinary least square method. There is another way which is called MLE, maximum likelihood estimate. Luckily for linear regression, both of them becomes equivalent. For maximum likelihood estimate, you need to know the distribution, which we generally assume for linear regression as normally distributed, right? And based on the distribution, we try to find the maximum likelihood estimate. But luckily, OLS also works for linear regression. So what I want to highlight here is that many times people say, oh, I am into statistics, I do not do a lot of optimization. Without optimization, you cannot do statistics. Any method you see, any point estimates you are trying to do, you need to understand how optimizing works. Like in this case, my function is given f a comma b, I equals to 1 to 5 yi minus axi plus b whole square. This is your prediction. Let me call it y hat. This is y hat and this is your actual. The difference is the error and you are trying to minimize the error square. If you look in terms of geometrically, what you are doing, this is the error, this is the error in the estimate, this is the error in the estimate, this is the error, and this is the error. Let me call it error 1, 2, 3, 4, 5. What you are doing, you are squaring these errors and summing it up and finding the minimum, because from these, this line can also pass, this line can also pass, this line can also pass. I want to find the line which will give me the minimum sum of squared errors. So what we can do, the A and B values which are given to us, we can directly put in here and find it, or simply you differentiate your f dash AB, equate it to 0. You will get in terms of, you will get 242A, assuming I have put all the AI's and BI's values, 42B minus 424 equals to 0. It will be a quadratic equation. You will get A equals to quadratic. You will get a normal equation. A equals to 131 by 82 and B equals to 73 by 82. So the equation line of the equation of the line is 131 by 82A plus 0.890. So you are able to fit a line which minimizes, because as I said, if there are points and through which I'm trying to pass a line, there are infinite number of lines possible. I'm looking at the one which minimizes the sum of squared errors. So you see one of the, statistical method. Now data science is more popular, but I would say it uses least square method or optimization to find the parameters values. Similarly, when we will study next constraint optimization, we will see the KKT condition, where we will see how it is used in lasso and ridge regression or support vector machine. So all the, the underlying mathematics, if you look at most of these methods which you are studying or using, is based on the optimization. So I will stop here. I will start constraint optimization tomorrow. If you have any questions, we can discuss now. So,
Sam, I have one question. Whatever till now we have discussed about this unconstrained optimization part, everywhere we assume that differentiability is present at that point. But what is the scenario when it is not differentiable at that point?
That is why we will use numerical methods. So first part of it is how do we solve all the differentiable function which we can convert into closed form. Second part of this nonlinear programming, what we have studied, there will be both. Many of them will be suitable for pseudo-convex, many of them will be suitable for convex, because even if it is a convex function, not necessarily you will differentiate and equate it to 0 and get a closed form solution. You agree?
Yes.
So in that case, we use numerical methods, like we'll discuss many kind of method. Wherever we'll classify into two parts: gradient free method and gradient based method. Gradient based method again is only applicable to your differentiable functions, and gradient free method is more of, I would say, heuristic kind of method, which are more appropriate for any kind of function you are trying to optimize. I mean, just to give you a simple overview, suppose a function looks like this. What I will do, I will divide it into many parts and I will calculate. Although computationally it is very expensive, but this is the most naive method to start with. You find various values, and the various values you have find, look at which one has the minimum value. That is your answer. Second method, we will look at divide into two parts. Look at which part has a minimum value. Then go into that part further divided, which we call dichotomous search or binary search. But all these methods, the study of non-linear programming, you will see it is not apt for every functions, and that's why we have what we call heuristic method, which is genetic algorithm, particle swarm optimization, simulated annealing. These are more appropriate for local search or global search kind of method. So that is another course, but I will cover whatever we can solve with non-linear programming techniques.
Okay.
Does that make sense? Since you have mentioned, let me just, actually I was just preparing some notes for another class, and I will show you something interesting. Just give me a second. So if you, I mean, given many of you have already worked at places, if you classify optimization algorithms, where is my pencil? This is just for, since you have mentioned, and I was just discussing it with one of the class, so I thought I will tell you. There are two kinds: deterministic and stochastic. This is the two broad, at least from classification perspective, we can divide optimization algorithm in two parts: deterministic and stochastic. Deterministic, what is the most common local search technique you know? Hill climbing, have you heard?
Ant colony?
I mean, ant colony is little, the most I would say most simplest local search technique is hill climbing. If you take any course on algorithms, the hill climbing is the most basic technique. But let's look at deterministic. What are the scope? First one is simplex, which you have studied in linear programming. If I go to non-linear programming, I have gradient free and gradient based. In gradient free, we have uniform search, dichotomous search. We will also see hook and Jeep for multidimensional. And as I said, the most basic one is hill climbing. I'm trying to hit, I have been told that treasure is at the top of the hill and I'm trying to get the treasure. So I'm just evaluating my neighborhood. If I'm doing better in one direction, I keep moving in that direction. When it comes to gradient based, that means I need this differentiability. So we'll look at Newton's method. We will look at steepest descent. Now, when you come to stochastic, generally we look here, we are looking at the algorithms which are non-differentiable. So here you will get heuristic and meta-heuristic. Heuristic mostly trial and error, problem specific. Meta-heuristic can be applied to many such problems. So they are not they are problem time agnostic. So here you will have population based and trajectory based. So trajectory based is extension of your hill climbing. Here you will get simulated annealing and all that. Population based, you already have seen genetic algorithm, PSO and so on. Okay, so this is a crude classification of optimization algorithm. What we are only focusing on this part in this course. Is this clear, Abhijit?
Yes, sir.
Okay, guys. So I stop here. We'll meet on Thursday again. Very happy Republic Day. Sorry, I was not that enthusiastic today because of my sore throat, but hopefully it will be fine by Thursday. Thank you, guys.
Happy Republic Day to you, sir, and to all.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.